So in this chapter, we'll talk about the electromagnetic wave, and then the energy transport, and also the Poynting vector, and the radiation pressure, polarization, reflection, and refraction, total internal reflection, polarization. So yeah, you may feel like these parts are quite independent with the previous parts. And yeah, so first of all, I will just follow the textbook to introduce what is EM wave and blah blah blah, and then you will feel like that it is some sort of weird because you don't really know why. And after presenting all this, and then in the next lecture, yeah, I will also tell you how to derive all those formula. Actually, we need to solve the wave equation to really get the EM wave solution. And then you see some other equation. The reason or how to derive some other equation as well. So yeah, so I will also have supplementary notes for that, for this chapter. And in for the later part of this chapter, you feel like the polarization is quite independent. And then for the refraction, TIR or something like that, I suppose you should have learned it in high school. So I just talk through it briefly. Okay, so when we talk about electromagnetic waves, so this is just a joke. So this is the genesis. If you study in a Christian school, you should have learned the Bible or memorizing some of the Bible. So in Cantonese, it is like 起初神創造天地，地是空虛混沌，淵面黑暗，神的靈運行在水面上。神說要有光，就有了光。So I cannot even memorize it in Mandarin because yeah, you know, when you try to memorize something in a specific language, you cannot. It's not easy to translate into other language. So this is just a joke. If you have know the Christian, yeah, so you may have learned it. Maybe this is the NIV version. Maybe you are the Catholics. You are from the Catholic school or something. Then the Bible will be written in a different version. So I don't read them. Yeah, but actually, I would say the light is a type of the EM wave. Of course, there are some other EM wave, which is like, for example, the Wi-Fi is a type of EM wave. When you use the microwave oven, is of course the EM wave, and some other wave are also the EM wave. So I suppose I have shown a similar graph before. I'm not sure in which chapter, maybe in chapter 21 or the beginning chapter, or I don't really remember, maybe yeah, but actually I show this similar graph again. So this is called the Maxwell's rainbow. It tells you that actually inside this range, all of them are electromagnetic waves. So in a science point of view, so this is from a belief point of view. Yeah, so here, so when we talk about the EM wave in a science point of view, so in the very middle part, so you can see the rainbow. So you will feel that this is the visible light. This is the visible light. So you should have memorized red, orange, yellow, blah blah blah. So this is the visible light with the order of the wavelength. So for the red color, it has the longest wavelength, and for the violet, it has the shortest wavelength for the visible light. And out of the so for the whole axis, all of them are EM wave. Only this part is visible by human eyes. And out of this range, you will see that this is infrared, in Chinese 红外线. And for this part, it is ultraviolet, 紫外线. And generally, so you can see here, this is wavelength. So if it is to the left, which means that the wavelength for the EM wave is longer, and to the right, the wavelength is shorter and shorter. And simultaneously, this is the frequency. And you can see that to the right side, the frequency is higher, and to the left side, the frequency is lower. Yeah. So, of course, the wavelength and the frequency will satisfy a relationship like C equals F lambda. C is the speed of light, C is the speed of light, F is the frequency, lambda. So lambda is the wavelength, F is the frequency. So they multiply to be a constant, which is called the speed of light. So as I mentioned, light is a type of the EM wave, but all the EM waves share the same wave speed, which is C. Yeah, actually all the EM wave will go with C in the vacuum or in the air will be barely the same. So in the Maxwell's time, the mid 19th century, 18 somethings. So the visible infrared and ultraviolet forms of the light were only electromagnetic wave known. So at that time, they don't really know that part of it because the human eyes cannot see that. So the spurt on by Maxwell's work, however, first, so this is Hertz. So you see the SI unit for the frequency is Hz, which is the short form for this name. So discover what we now call the radio wave, and verify that they move through the lab at the same speed as visible light, indicate that they have the same basic nature as visible light. So we now know a wide spectrum of electromagnetic wave, the Maxwell's rainbow. So as you can see here, so we have longer wavelength and we have a larger frequency on the right side and longer wavelength on the left side. And also, actually this semester, I don't have time to talk about the modern physics, but you know the energy for a photon or something like that will be like H times F. Or sometimes the textbook will be written as H nu using the Greek letter. But actually these two, I don't think the difference between them. Which means that if the frequency is higher than the energy density, or at least the energy density should be higher, which means that these are so-called high energy. So we have high frequency on the right side, which means that we also have high energy on the right side. So yesterday I mentioned the high energy particle, mentioning the gamma ray, something like that. So actually the magnetic field of the Earth actually shielding us from some sort of a high energy particle. So we can see gamma rays are the highest energy particle, and we can also see X-ray. So you see X-ray can see through our can see the bone, whether we have some abnormal situation inside. So X-ray, as much as it has a small wavelength, so it can go through something easier. Yeah, so you can check between some of the tissue to see through the body. Yeah, so this is why the high energy particle dangerous, because it can go through and directly go inside the body. Yeah, and yeah, for the lower frequency, you can see here is around just say here 10 to the 9th power. 10 to the 9th power, if you know, it is actually the gigahertz level. Gigahertz level, or maybe this is a 100 megahertz level. So 10 to the 8th power is around 100 megahertz. So if you like to listen to the radio, if it's not too old school, so you will sometimes hear the advertisement to say, oh, it is, for example, the Macau radio station is 100.7 megahertz, 100.7 megahertz. Yeah, and yeah, so for the FM radio, it barely use the megahertz level around here. Yeah, maybe the SAM radio also use the similar frequency. And here, 1 gigahertz, around it, we will use the 2G or 3G communication system, or even 4G. The 5G, part of it use the gigahertz level, and also it use something like 20 or 30 gigahertz. So for 5G communication, it not only use this part, but also this part use something like 30 gigahertz. I don't really remember the exact frequency band, maybe something like 29 gigahertz, but for simplicity, you can just consider it's like a 30 gigahertz, which is quite enough for you, because most of you are not ECE students, so only know this, you are already better than the others. So it's like, yeah, so the 5G not only use a few gigahertz range, but also the tens of gigahertz. And this part we will usually call it the millimeter wave. Millimeter wave. In Chinese, it is called 毫米波. So, and actually you can see here, the wavelength is meter. So around this level, you can see the wavelength is around is approaching 10 to minus third. 10 to minus third is millimeter. So at this level, we'll call it the millimeter wave. This level, or maybe for some of the circuit, they design for 60 gigahertz, which is even closer to the millimeter level. For 30, maybe it is like around here, which is like more than a tenth, but less than 1 millimeter. So for 60 gigahertz, it is even closer. So you can see if you just plug in Z equals 3 times 10 to the 8th power, and then you plug in the frequency, you can check a more accurate wavelength. So this is related to the communication standard. So we will use lower frequency for the AM, FM radio, and also TV broadcasting. We'll use something like the several hundred megahertz band to transmit the TV signal. Because for lower frequency, it can carry less information. It can carry less information, which means that, just say, if you try to download a video, then you hope the speed to be fast enough. so that you do not need to break too much, or you don't need it to buffer for a long time. And in that case, you will hope to use a higher frequency so that it can carry more information at the same amount of time. However, for the higher frequency EM wave, it cannot go through a longer distance. It will start to decay. It will just start to decay, or maybe it just shoot on the wall, and then it will be absorbed by it. So for maybe you can feel it like if you use the 2.4 gigahertz band, usually you will feel like the signal is stronger. If it is a 5 megahertz band, so for Wi-Fi, you will see you can generate a 2.4 gigahertz band signal and also the 5 gigahertz signal. Actually, the 5 gigahertz, if the signal is strong enough, the throughput or the speed can be faster. However, if you are not actually facing the router, then the signal can be decayed. Maybe I just put it under the desk. You cannot see the router directly, then you'll feel like the signal for 5 gigahertz band will be much weaker, because when you try to shoot on the wall and then scatter back, the signal will attenuate a lot. And of course, for the broadcasting, using a megahertz or several hundreds of megahertz, it can broadcast for longer distance. So for radio or TV signal, they will generally use the few megahertz. So, or even in the past, the 2G, 3G, they generally use 800 megahertz, 900 megahertz. But now we are chasing for larger bandwidth so that we can transmit data in a faster speed. So for example, the Wi-Fi will use 2.4 5 gigahertz band, or even the 5G, they would like to have very high speed data transmitting. They will try to chase for the 30 gigahertz. So for the 30 gigahertz signal, it can only transmit for several centimeters, something like that. And they probably need an antenna array, something like they will have antenna like this. On the same plane, they have maybe like a 64 antenna in a plane, and then they try to transmit data towards one direction. And then you feel like all the signal are add together in the space. Yeah, because the millimeter wave will attenuate too fast, so they need many antennas to transmit the same data at the same time, so that the transmitted power is large enough. They hope like this. Yeah. So just tell you something about the communication, because yeah, my PhD research is about the wireless communication. Okay. So yeah, so here we talk about the electromagnetic wave. So the traveling electromagnetic wave. So we assume that there are some energy source, try to input some energy to this like RLC circuit. And in chapter 31, you know that this circuit will oscillate in a certain frequency. Of course, the real transmitter wouldn't be like that. It is just a demonstration. It can just oscillate at a certain frequency. But for a single frequency, it cannot carry anything, carry any useful information. We need something called a modulation, the 调变, to really carry data. For example, if you see AM or FM, the M means the modulation. The M means the modulation. A means the amplitude. FM, the F means a frequency, and then M means modulation. So FM means frequency modulation. AM means amplitude modulation. We would like to use different amplitude to stand for different information, or maybe we can use a different frequency to stand for different information. But if you just transmit a single sine wave, then it cannot carry anything useful information. But it's just for demonstration. So if we have energy input to this RLC circuit, of course it will oscillate in a certain frequency. Could be calculated by this RLC value in chapter 31. And through this transformer, this frequency can be transmitted here. And as much as this is a sine wave, which means that we can couple some of the magnetic wave, or should be the magnetic field, to the secondary coil. And in this case, this is an antenna. This is an antenna. And then as much as the current is time varying, which means that it will generate a time varying magnetic field. And the time varying magnetic field, due to the Faraday's law, it will generate a time varying electric field. And then the time varying electric field will further generate time varying magnetic field. So it will generate a EM wave, so on and so forth. So it's like a wave propagating through the space. So an arrangement for generating a traveling EM wave in the shared shortwave radio region of the spectrum, and LC oscillator produce a sinusoidal current in the antenna. So this is a demonstration. This is a symbol of this antenna, which generates a wave. P is the distant point at which a detector can monitor the wave traveling past it. So this is the antenna. So as much as a EM wave, it will transmit through the space, and at some point it will sense the variation of the EM wave. And one point I can also mention is that for the design of this antenna, it should be related to the wavelength of the EM wave. So if you see the very old class radio, it will have a very long antenna, maybe this long. So it should be related to the wavelength. So you can simply calculate the wavelength here is around 1 meter. It's around 1 meter, but at least the antenna should be like a quarter of the wavelength. So as much as the wavelength is around 1 meter, so the antenna should be at least like 20 or 30 centimeter long. And even for your mobile phone, if you really need to absorb some of the FM signal without going through the internet, then you should connect the earphone so that it can absorb the FM radio. The meaning for that is it's like the earphone is like an antenna, because the line, the audio line for the earphone is long enough to act as the FM signal antenna, something like that. Yeah. But of course, for the Wi-Fi, some of the router you can see the antenna like that, so it will be around 10 centimeters, something like that, or maybe 5 centimeters, something like that. Yeah. And for the recent router, you will also see there are multiple antennas, and the separation for them also related to this lambda over 4. If the antenna are placed close enough, then they will not be useful. Yeah, so maybe we just stop here today.